All right, welcome back, everybody, to another episode of the Additive Snack Podcast. I'm your host, Fabian Alefeld, and today we're diving into the transformative power of the world of heat exchangers in combination with additive manufacturing. Joining me, therefore, today is Michael Fuller. Michael is the founder and CEO of Conflux Technologies. If you've been in the additive manufacturing space, you've seen a Conflux heat exchanger for sure. They've been, I would say, from what I know, the first ones to really display the true potential of thermal management in the additive manufacturing space, and are really redefining how we think about performance, efficiency, and innovation in the heat exchanger application space. So therefore, today we'll talk about Michael's entrepreneurial story and how he started Conflux, which I think is a quite interesting journey. We'll talk about the advantages of additive manufacturing heat exchangers. We'll talk about performance enhancements, but also what the future holds for additive manufacturing in that space, and of course, for Conflux. So therefore, without any further ado, Michael, welcome to Additive Snack.
Thanks, Fabian. Nice to be here.
So like I mentioned, I'm always interested in founder stories, and I'd love to hear yours. How did you get into the heat exchanger space, and then how did you get into starting a company called Conflux?
There's a few different tributaries that led to the founding of Conflux. Firstly, for my whole childhood, watched my father run a business, that he started in the 1970s and ran through the 1980s. It was actually an engineering business, and it was the exposure that I had to that was one that really turned me off the idea of running my own business. So I pretty much swore that I never would do that. And I had a passion as a child in motorsport, and realized sort of at the age of 10 that I wasn't naturally fast enough driving the go-karts and racing the go-karts, but still loved the sport and really wanted to have a career in motorsport. And then it was around the age of 12, I think, I'd always answer when adults would say, "What do you want to do when you grow up?" I kept on persisting, saying that I want to make racing cars. And then after a couple of years, my dad said, "Well, how about you write letters to the Formula One teams and ask them what you need to do if you're serious about doing it." So I did. I wrote a letter, I drafted a letter saying, "My name is Michael Fuller, I'm 12 years old in Australia. How can I come and work with you in Formula One?" And a number of them wrote back, or they got some of their senior people to write back. And I got a few letters, and one of them was very prescriptive that said, "Okay, if you want to work on the cars, then you need to go and do an apprenticeship and then work in the lower formula, and then you can come over to Europe and see if you can work in Formula One as a mechanic. But if you want to design the cars or be involved in the engineering of the cars, then you need to get an aerospace or a mechanical engineering degree and then work in lower formula and then come over and see how you go." And so I did some work experience, discovered that I didn't want to be a mechanic. I think I was a little bit too cerebral for that. And so it was quite a prescribed path, and I needed to get this engineering degree, and so I needed to do these particular subjects at school. And so I really, from a very young age, followed a specific path and trajectory towards motorsport, and then was very fortunate enough to work for about 15 years based in Europe in the motorsport industry, covering a number of different series from Formula One and Le Mans endurance racing, as well as the World Rally Championship.
Super cool.
Yeah. And so how did that lead to Conflux? Well, there's a couple of factors there. A lot of exposure to heat transfer and the opportunities to improve heat transfer efficiency. That's one of the key elements in motorsport. You've got very high performance machines, and the machines generate a lot of heat, and that heat needs to be removed in order for those machines to continue operating. And also there was early adopter exposure to freeform fabrication, rapid prototyping, 3D printing, and then ultimately the reference is then additive manufacturing. And so I had exposure to the technology from a very early stage. But one of the inflection points for me was when I realized that there was a significant implication beyond just the geometric freedoms that were afforded by additive manufacturing. And this was in the Formula One industry, it was more, not so much a business case as it was what's the first order of performance and how can you use this manufacturing technology to support that first order performance. And that is the aerodynamics of a Formula One car are the most important performance factors. And so at that time, it was how do we make aerodynamics better, and that is staying in a wind tunnel for longer. And so one example is the brake duct assembly in Formula One cars. They were made at that time with very complicated bonded and glued assemblies of carbon fiber components, all of which needed to have very complicated mold tool assemblies. And then all of this, for example, one corner of a Formula One car, so a brake duct on the front left corner, that might have, at the time, may have had 60 or 80 pieces of tooling, which is then symmetrically mirrored on the right-hand side. And then you've got the same again on the rear brake ducts. And so you have quite a long lead time. And that lead time is from a design freeze. And so additive manufacturing, or at the time it was 3D printing or rapid prototyping, that allowed much longer in the wind tunnel, where the trade-off was just a bit more weight, because you could manufacture it without the lead time of all of the tooling. And so, an additional 2 or 3 weeks in the wind tunnel, where you could get a lot more performance that would be better, more beneficial than the extra 100 or 150 grams of weight.
Huh. So it was a supply chain case really in the beginning.
Yeah, I mean, it was
extending the time for iterations and redesign potential.
Yeah, exactly.
By not having to order parts as early.
Well, yeah, and yes, there was the shape, having some additional shape, but the reason that the complexity of the tooling was there was because you still were able to make very complex shapes in laying up carbon fiber and bonding these assemblies together. However, the first order performance is the aerodynamics, and getting more time in the wind tunnel really was the primary thing. So when that realization was there, and the heat transfer opportunities and really heat exchangers, whether it's a car radiator or an intercooler or a box for mounting electronics and having integrated cooling there, there's one fundamental, and that is that the performance, the heat transfer performance is dominated by the geometry. And quite often that geometry, there's surface area, which is the key number one influence. But then there's a trade-off, because the more surface area you have, maybe the more pressure drop or the more losses you have as you try and pass the fluids over the heat transfer device. So additive manufacturing offered new opportunities for geometry, coupled with the potential of a business model implication, and really the maturity of the technology as it was in 2014. I perhaps was classically early. I thought that it was more mature than it was in terms of its industrialization. However, quite early on in the piece, it became apparent that there was a lot of work that hadn't been done, and that if we were going to make this business work, it needed to be done by us. So we have driven a lot of the technology in the specific way that we need it. So this is really talking about very thin walls, small feature distance, so high resolution, but written large across build volumes.
Interesting. So out of Formula One, you decided that there's a market for additively manufactured heat exchangers.
Yeah, I mean, I didn't decide as much as scratch the surface and discover. So the founding story really was one where I'd moved back to Australia for family reasons, and after a clumsy incident, had a broken ankle, was at home, had my laptop there. I wasn't able to put any load on my ankle for 10 weeks, and with a busy designer's brain, got designing and came up with a concept for a heat exchanger that could only be made by additive manufacturing. And having designed lots of things, I know that many bad designs and occasionally have a good one. This one I thought was worthy of throwing a bit of money at to see if I could, firstly, if I could make it, because it was, at that time, it was not clear if the manufacturing technology was ready to even manufacture something. And as it turns out, they were quite limited. In Australia, at least, there was limited options in terms of metal AM machines that were able to do what we needed to do. There were some in some universities, but there was a service bureau or a contract manufacturing company that was trying to get up and running. And we used their M280 EOS machine, I think they had, and managed after a few failures, managed to tweak the design and tweak the process to get a heat exchanger that was leak proof or gas tight, albeit a very early sort of technical due diligence or technical feasibility build. But yeah, that was really the initiation of it. I thought, well, I don't want to go back to Europe into motorsport. I really came away satisfied with a remarkable 15 years, and then did what I swore I wouldn't do, and that is start a business. And I sort of put myself through an unstructured but online course or series of courses in starting up businesses. There was a bit of a startup fad happening at the time, and it was quite apparent that this was going to be a relatively heavy capex business to start. It was not. I wasn't building an app. I wasn't going to be flipping a business in 18 months. That's for sure. I was aware of how many unknowns there were, and it became, as we went on, it became more and more apparent that there was a hell of a lot of technology that needed to be tamed and understood and mastered. And so really, the term hadn't been created at the time, but Conflux is definitely in the hard tech part of the startup landscape, because the technology is really difficult. The application of additive manufacturing in this sort of space is extremely challenging. And ultimately what we're doing is bringing a nascent manufacturing technology in terms of its industrialization, applying it into a market that has already got 150 plus years of incremental development and optimization, and where we're going into large enterprise customers saying, here's our better technology, and they quite often they say all they see is there is a lot of risk, and so we need to make our performance so compelling, and we need to make our products so affordable that they have no alternative than to overcome that adoption risk that is inherent in large organizations.
Interesting. Yeah. It is really interesting that, especially in the additive space, you guys seem to be one of the first companies that were started around an additive manufacturing application, and not an additive manufacturing software or hardware solution. And really, you were the ones that trailblazing that path for the industry, right? Which year did you start Conflux?
Yeah, so I don't think we could claim to be the first ones to align heat exchange and additive manufacturing as a specialist. I think High ETA in the UK did that, albeit with a bit of a different business model as they launched. They eventually got bought by Meggitt PLC, which then got bought by Parker. So we don't see them active in the market particularly, but I would say that they were earlier out of the blocks than we were. GE, before they created GE Additive, GE were doing a lot of work originally with Morris, and then when they'd taken over Morris, they were doing a lot of work in the AM-based heat exchanger field, but majority for their own internal purposes. But I think we were the first to have a very market-oriented business. So we've got from a clean sheet company, we've had a very, very much a customer orientation. We've got some government grants along the way, but it's by far and away the smaller element of the business. We've got a very strong customer focus with our pipeline of customers ever increasing, a very sort of specific customer relationship management approach. And we have that, like an actual business being the prime goal, not one that is fed by government grants, or one that is like an AM curiosity. So actually, it's probably important to say that we characterize ourselves as a heat exchange company, not as an additive manufacturing company. We happen to use additive manufacturing as an enabling technology, but to your question around the application first, we definitely are an application first company, and we happen to use AM because we see really specific competitive advantages there. However, should a new technology come along that, like does away with those competitive advantages that we have in additive, then we will pivot if need be. But at the moment, we haven't seen that, because, like I said, in order to have and grow this into a successful company, we've had to keep a very clear eye on the AM side of things, providing performance potential of heat exchange, but the affordability is extremely critical. And so we spend most of our R&D dollars on driving cost out of our product so that we can make them more affordable, so that we can scale these energy efficient devices across the globe, deploy them across the globe at scale.
Interesting. Yeah, I'm sure it's a challenge by itself. Before we go into the cost and productivity aspect, which I think is super interesting, mentioned you walk into a door of a potential client, and they always compare the conventional solution that they currently procure with an additive solution.
Yeah.
Can you talk a little bit about the value proposition of a additive heat exchanger? What are some of the performance improvements and other value adds that you're bringing to your clients?
Yeah, so absolutely. I mean, you'll find that I veer quickly into cost regardless, because that's the reality of bringing an application to a new technology into a space. But, it's a classic case of what's a product and technology market fit. So we need to continue to mature the underlying technology, but make sure that we're applying our technology into the right markets at the right time. So this is in terms of productivity, in terms of unit volumes, and all of these sorts of things. The sort of classic economic sort of metrics, but just purely from a performance perspective. So we need to, if we're going to introduce new technology, to overcome this technology adoption risk, what I was talking about, you have to have these two elements, really a very high performance, where the value sell is how it's done, not the commodity sell. And you then need to make it affordable. So the value cell needs to be based on the performance of the heat exchange, and these are sort of broken down into relatively three simple legs of a stool. You have the actual heat transfer, if it's 2 fluids or 3 fluids, or even if it's like a heat spreading vapor chamber, whatever it may be. You have the heat transfer that occurs. You have the losses, or the pumping losses, that occurs as you pass the fluids over the heat to do the heat transfer. So we can characterize that as the pressure drop across the system, across the heat exchanger. And then you have the weight, or the packaging volume. And you generally have a trade-off between these. Like if you want to have low pressure drop, then one way to achieve it is to have a certain amount of surface area, but in a bigger volume. And so then there'll be less restriction to the flow. But if you want to have high heat exchange, you need to get more surface area in there. And so then you get, quite specific into the weeds and into the core of the heat exchanger, where you want to be transferring as much heat as you can per unit area of surface area. So you want to then say, okay, well, what are the advantages that additive manufacturing can bring over traditional manufacturing? Well, in the geometry, we have three-dimensional surface geometry in our very small, high-resolution features. We also are able to have very small feature distances, and we're able to tune the geometry Not in all cases, but in some cases you'll have heat transfer fluids that are going from a very high temperature to a very low temperature through the device, through the heat exchange device. And as they're changing from high temperature to low temperature, the thermal physical properties are changing. So their density might be changing considerably from high temperature to low temperature. And with additive manufacturing, we're able to adapt the geometry through the fluid domain to intensify the process, such as we're able to make a heat exchanger smaller that's able to do the same amount of heat transfer. So this is where the advantages come. And this is probably where we're, a heat exchange company first, and we use additive manufacturing. We don't make particularly AM sexy looking shapes. Like a lot of the time there's a very simple form factor. It might be a cylindrical form factor, or it might be a rectangular cubic form factor. We do custom morph topology when we need to for specific custom applications, but the heat transfer fluids don't care about additive manufacturing. They don't care about like sexy, twisty, shapes of gyroids and blah, blah, blah. They just want to, for low pressure drop, the fluid coming in at the entrance would like to have a clear run to the exit. Then you have low pressure drop. For heat transfer, it wants to have a lot of surface area. So what do you need to do for a lot of surface area? You need to have, lots of walls and lots of fins. And these things have been created in heat exchangers for a long time, and there's a good reason. It's a very effective way to transfer heat. So it's really bringing the advantages that additive can bring and applying them to what is first principles thinking from a heat transfer perspective. And that is trying to induce more heat transfer per surface area without increasing the pressure drop. So that means not trying to turn the flow around and around and around, trying to induce the mixing that you need to get to break up thermal boundary layers through the fluid domains and this sort of stuff. And this is how we use additive. And it's on the inside rather than in the external shape.
Interesting. I disagree though. I think your parts look pretty sexy, especially when they're cut open. I was just at your booth at Formnext, and I thought every individual application you had on there is a very inspiring application for, I think, many people that see them and are even trying to understand additive, because it really shows the true potential of the technology.
Thanks. I appreciate that. But I think there's a if you know kind of condition. If you're aware of how difficult it is to do what we do, then there's a beauty in it, because there's an appreciation for how bloodied our heads must have been banging it up against the wall trying to tame the technology and make it do what we do. And there is a lot of blood, sweat and tears that have gone into the R&D to be able to do it. And we continue to push those boundaries all the time. But being able to create gas-tight heat exchangers when you might have 200,000 fin features that are connecting to tube-like structures with thin walls as well. So you might have 400,000 fin connections, but you're building it layer by layer, over 10 or 15,000 layers or whatever it may be. And if you have one pore that is too big and then you've got a leak, then you find out at the end that you've got a failed build. It looks great, but then there might be one pinprick leak, and this is where it becomes very interesting and challenging. And making a heat exchanger once is okay. Being able to do it repeatedly is a whole nother story.
Mm-hmm. I do want to talk about volumes and scale. Maybe before we go there, just briefly on numbers. If we talk about performance increase, for example, thermal transfer, what can people expect on an improvement of a Conflux heat exchanger compared to a conventional heat exchanger? Maybe if you want to pick an example of a certain device that you guys optimized.
Yeah, so it's a classic, how long is a piece of string, or what starting point do you want to choose? So if you compare us to a very cheap, low performance heat exchanger, then you can say, all right, well, you've got something that's 1/5 of the size for the same heat transfer. This is a situation where you go, wow, 1/5 of the size? That's like, I'll buy it for sure. But then you say, yeah, except that one is mass produced 300,000 units a year, pumped out of an automated factory, and it'll cost you $50. And the one that's 1/5 of the size is going to cost you $5,000. And so you go, okay, is that a fair comparison? Well, it is a fair comparison, because if you don't care about cost, you only care about size, then that's the situation. But at the other end of the scale, you say, okay, well, what's the best performing heat exchange technology alternative to the Conflux technology? And that's where you start getting into, these microtube, hypodermic needle type heat exchange cores. And a number of companies now produce them, but originally I think that it was Mezzo Technologies out of the US that sort of were the first ones that I was aware of. And this is amazing technology. You hold these devices and they're super lightweight, and you can't believe how much surface area is in there, and they perform at a very high heat transfer level, but their cost asymptote is really high. These things it's very difficult to automate the production of them. The yield on production is very low, because the joining of these like tens of thousands of hypodermic needles, joining them to get seals is extremely difficult. And so what we see over many years, and many companies attempting to do it, is a really high cost asymptote. So what we've done with Conflux is that we've aimed there and above for performance at sort of this microtube level of effectiveness, where Formula One cars and certain aerospace industry and certain low volume, high value type applications, that performance is the benchmark that we've been aiming for, and we now exceed that in some instances and are just below it in other instances. But we're there or thereabouts with heat exchange performance with microtube heat exchangers. But our cost asymptote is already lower, and we're driving cost out.
Wow.
So we're making it more affordable, such that we can, not straight away now, but in the horizon that we can see, we're going to be competing much more by bringing this 1/5 the size, but instead of being 100x the price, we'll be 10x the price. And so this is not going to be us putting Conflux heat exchangers as car radiators for a VW Golf. This is not the application. Those are large and they're cheap. And for additive manufacturing, I don't see large and cheap occurring in the next 5 to 7 years. However, I do see a pathway to structural cost decline without compromising performance. But it requires not just us to realize that.
Sure. Yeah, there's many parties involved in bringing that down. But it is very interesting that you're able to meet or exceed the high performance of, very complex, conventionally manufactured heat exchangers, but at a lower cost.
Yeah,
So,
I wouldn't characterize them as conventionally manufactured. Those are heat exchangers that are more in the craftsman sort of element, where they're a lot of hand assembled, manufactured, whereas the conventional manufacturing of heat exchangers is very automated and really has achieved economies of scale. However, one element that we haven't talked about is the flexibility of it. So one of the things that our customers really enjoy when they work with us is the rate of innovation. And this has got a lot to do with the decoupling of complexity from tooling. So a lot of heat exchangers get specified or designed via a lookup table, and then a system will be compromised based on the availability and the lead time of that heat exchanger. So quite often heat exchangers are oversized, and then the packaging is compromised because of the in order to change the heat exchanger design, if you need more tubes or if you need more fins or if you need it to be an odd shape or anything like that, the retooling implications are so significant that they just don't even go there in their considerations. They just go, oh, this is a heat exchanger, it'll do the job, we'll work around it. Whereas with Conflux, we are in production down the hall here with heat exchangers of multiple different designs. Some of them are going through proof of concept iterations in pre-production prototype development, and they're manufactured in the same manufacturing line as our R&D work happens and as our production work happens. And the fact that we can do that really brings down the total overhead, and it opens up a lot of opportunity for our customers to derive value that they beforehand wouldn't have even considered possible, which they can then take to their customers. So it's this is also one of the real benefits that we bring.
Yeah, it makes a lot of sense. You're adding flexibility to the design teams to focus on some of their core applications versus designing around a standard off-the-shelf heat exchanger in that regard.
Yeah, so we have basically two primary streams of offering that take advantage of it. One of them is that we've got a number of product families that we already have done the base R&D and product development work on, and we can configure them to the specific needs of the customer. As long as they're okay with the form factor, which has already been set and established, maybe some inlets and outlets are in different positions, something like that. Or the mounting might be a little bit different. But it's a rapid configuration, so the number of tubes, the height of the fins, the spacing, the this, that, and the other can be all configured for their specific requirement. And then this is low lead time, low non-recurring engineering, get to a proof of concept or get to their first prototype early, and then they can get into durability testing early, etc., etc. And then the other offering is a fully customized solution, which is maybe, like a customer comes and they've got a very strange set of boundary conditions. It might be like a cryogenic application or something like that. And then there's a longer development program where we look into our library of IP and we try and apply that and customize it for the specific needs of the customer. But the form factor might be quite different and the environmental conditions might be quite extreme, something like that.
Okay.
Yeah.
What does that development process look like in detail, where a customer comes in, has a certain design space, has certain performance requirements? How do you guys approach that in order to get to a solution from a design, from a manufacturing process, and also from a testing perspective?
Yeah, so it starts a ways before any sort of technical people have got involved. We've got a marketing team that's part of the commercial business unit. So the marketing team looks through our organization, finds case studies, finds specific work that we've done for particular markets and generates and deploys a lot of content to describe to our markets and to our potential customers who we are and what we do. This generates quite a bunch of leads, and these leads get qualified through and then passed over to business development into a pipeline or a funnel. The business developers will then engage with the customers and look to understand, problem and time frame to a solution. And when certain qualification of the opportunity is made at the business development level, we have a technical team that sits within the commercial group. And this is a solutions team, because ultimately what we're talking about, sort of unfortunately or not, I'm not sure, but we're talking about a technical sale. So bringing the solutions, they're technical solutions to technical problems. And so the earlier our engineers and our solutions engineers can be with customers, the better, because then we can understand their problem and we can describe a solution and a calculated solution with, that's been backed by multi-physics modeling, whether it's CFD or finite element stress analysis, whatever it may be, to a certain extent, where we say, okay, we've described we've described your problem in a way that we can understand, and here's a solution, a potential solution, and this is how long it would take to arrive at, a deliverable like this, and this is how much it would cost. And then a purchasing decision is made by the customer, and once we have received a purchase order, then that potential solution and pathway to that solution gets handed over to our technical operations group, which again is a team of thermal calculations experts, design engineers, and AM process engineers. And that sort of triangle of engineering disciplines work together in sort of rapid cycles to realize the solution. And invariably we get into production in relatively short order, at least prototype production. And there might be some trial builds for some specific areas of geometry that are of a concern, but then we'll move through into a proof of concept prototype quite quickly. Now there's a bunch of testing requirements to prove that concept. Quite often we'll take on the burden of those testing requirements, but some of our customers have their own laboratories that they believe the results in, and they'll want to test our solution in their test facilities. So we work with different customers in different ways because some customers have all of this facility, others rely on us to provide that. Once we've gone through proof of concept, normally no one's investing in a proof of concept if they don't have a production pathway understood. And so we'll be working with the procurement departments from earlier on in the proof of concept, working with procurement departments towards a production rollout. And we have multi-year production supply contracts with a number of our customers. And those are, relatively mature processes that are sort of market dependent. So if it's an automotive process, it may be, running through a PPAP kind of program or something like that. And then there's the aerospace industry, which has got different hurdles that need to be overcome and different requirements from certification, et cetera, et cetera.
Mm-hmm. If you look at a Conflux heat exchanger, I think your geometric approach to heat transfer is, I think, very different to anything else that you see in the industry, where maybe a bit more standard geometries are being used. I think it's very obvious that you guys truly understand heat exchange and that you have a lot of experience and most likely IP in the design of very specific geometries. How do you approach that design process towards a certain application? Do you have predefined libraries? What does that look like? Also from a user perspective, how does Conflux get me to these high performance applications that I think are very different to anyone else?
So yeah, we've got a whole history, libraries of geometries that we've arrived at through a lot of R&D. So our IP portfolio is ever expanding, and it sort of is about a 25% expansion year on year for the portfolio. Wow. And that portfolio is made up of design patents, process patents, trade secrets, proprietary processes that we haven't patented, and really the way that we go about designing and manufacturing the designs. This is, aggregated into a portfolio of IP that we track and measure and analyze. The way that we arrive at solutions is really where we lean into the history, our understanding of our own geometries, and where the sensitivities to them are, where the applicability is. So for example, some of our geometries, we have figured out how to build this sort of three-dimensional surface geometry, but it's not applicable to all boundary conditions, and it's not the right choice for all circumstances. So we've got a very good understanding about where to apply what families of geometries within our library. So we'll quite often we'll look at the boundary conditions, and our solutions calculations engineers will look at the boundary conditions and say, okay, so we've got this background knowledge that we've built up, across these different circumstances. This element over here has got applicability because the flow rates and the temperatures and the thermophysical properties of this fluid are similar to this thing that was part of the generation of that part of our library. And over here we did this. So we've got these experiences, this knowledge, which is captured in our IP portfolio and measured and tracked. And so this database of knowledge really is the value that we bring to our customers, because we can quickly arrive at an optimized solution, or at least the start of an optimization that is far along the track towards the targets. And that is, that's the sort of that's the moat really, because it's our geometry, it's our understanding of that geometry and its application in the world across multiple different scenarios.
Super cool. Now, as I said, if you see a Conflux heat exchanger, you can tell you understand and appreciate the experience that you guys put into those devices. Let's talk about industries for a second. Which industries have adopted your technology first? Where do you see a lot of growth right now? What gets you excited when you look into the application space today?
So you do what you know first, and I knew motorsport. So motorsport was and still remains a very significant part of our market, of our customers. But that then leads into automotive more generally. So a bunch of technology in the EV development space, albeit that's really dialed back in the recent past with a number of automotive companies pulling back on their development programs. But the advanced air mobility space is a market that is nascent itself, but there is still a lot of development going on in that space, and there's some winners and some losers, and we're active in that space across a number of geographic markets as well. The space race is real, and we're in it and aware of it, and applying our technology in there as well. And aerospace as well. I mean, this is a longer burn. This is very long certification pathways, and different customers have different appetites for it in and across there. But we're active from the large OEMs as customers through to smaller tier suppliers, as well as smaller aerospace players. We also have some technology in industrial machines, be it MRIs, and there's some additive manufacturing machines that have our additively manufactured heat exchangers in them. And I would say the industrial space is less of an opportunity, I believe, because space constraints are not particularly strong. And if you can buy a larger commodity heat exchanger because you're not concerned about the space, then it's probably, you might be better off doing that because it's going to be cheaper. However, there are circumstances where space is really, really constrained and thermal limits are reached. If you look at the chips that are being produced now, the square area, or the heat produced per unit area, is increasing more and more. You're talking about multiple kilowatt heat needing to be rejected out of chips now. And so there's the on-chip cooling, but then there's also the management of heat in the semiconductor manufacturing machines themselves. There's a very, very highly thermally toleranced situation. So thermal management is there as well. So our problem, because heat transfer is ubiquitous, like the opportunity to improve heat transfer efficiency is first law of thermodynamics. It's a universal law. So the opportunity is limitless, basically. So our discipline is in remaining focused and making sure that we're communicating to the right markets that have got the right technology fit, product market, technology market fit for now and for the next 5 and 7 and 10 years. And then, as we've developed through that time, we'll be able to look further afield to see how we've developed the technology and how more applicable it is in different spaces.
Sure. And I'm also certain that as you as you grow and as the underlying additive manufacturing technology grows and becomes faster, cheaper materials, etc., and your cost therefore drops, you also unlock new application spaces just through productivity gains and cost reduction.
Yeah, for sure. It will be it'll be a happy day when the material cost becomes a significant part of the pie for us.
Yeah, I can
'Cause
imagine. Speaking of material, how do you incorporate a material choice into your design process? Because I'm sure that choosing a copper with higher connectivity over a aluminum improves your thermal transfer, but you have different wall thicknesses that can be achieved. So you may have a constraint in wall thickness and size. How do you balance that game?
Yeah, so the material choice is generally boundary condition and target dependent. So rather than choosing a material and then pushing that into a market, we generally will adopt a material based on a market pull. So we have to onboarding a material for us is quite a particular process. We develop our own material process parameters that are specific for the sort of geometries that we need, and the bulk material mechanical properties are not necessarily applicable when you get into the thin walls. So we have very particular processes that we need to go through to ensure that we have high strength and the elongation that we need to have, etc., etc. And we see, non-linear responses as you're getting into these very thin walls, because it's very, microstructure dependent, and how those microstructures created really does change when you get down into the thin walls. And when I say thin walls, I would say anything that's sort of less than 500 microns or half a millimeter. I would consider half a millimeter and above to be a bulk section.
Mm-hmm. Mm-hmm.
So you have these non-linear effects, and so we need to go through a material characterization and mechanical property and process parameter development simultaneously, which the output of that process is a set of design guidelines for our calculations and design engineers. Because then they can say, okay, for this material, our thermal conductivity, we've tested it to be this, our strength is this, our minimum wall thickness is this, our minimum feature distance is this. Now we can go and design a heat exchanger. And, a customer might have an application where they want to preheat helium using a really filthy and turbulent mixed up exhaust gas flow, and they want to straighten that flow, and they want to preheat helium, and it's very very aggressive chemical mix in the gas flow. So we need to have this material here, which is a Mon K500 or a nickel copper alloy or a high nickel alloy, something like that. And so we'll adopt that that material because it has to be that material for this application, and then that material we can apply it across the marine industry or the rocket industry as well, or oil and gas and blah blah blah. So there's got to be a business reason or a market opportunity for us to take on the new material, not just one customer in one circumstance. There's got to be a strong, compelling reason for it. And then our R&D team will go in and develop the design guidelines for that particular material. And then we can go into design and providing solutions for a customer.
Awesome. Yeah, it really, thanks for explaining that. That it to me really shows the complexity and the in-depth experience that you guys have, which, it's years and years and years of trial and error and building up that library and knowledge.
Yeah.
And I'm sure you guys aren't done yet. What's next for Conflux? Where are you taking Conflux into the next stage?
Yeah, it's definitely not done. We're only just getting to the start line. The next phase for us, so what we've got is ostensibly we have these high energy efficient devices, and without being too lofty, the improving heat transfer efficiency Different customers will use that efficiency in different ways, but ultimately the potential of it is to the benefit of everyone on the planet, but not if it's just in a few niche applications here and here and here and there. We need to scale for impact, and that's one of our key strategic themes as a company, is scaling for impact. And so solving that problem, our first proposal to solve that problem is to have these certified heat exchanger designs and manufacture and prove them and produce them for our customers. But then for them to scale, our customers to scale, they need to have the means to produce them, because if we're going to scale and deploy these heat exchangers at scale, that needs to be done not just by us. So our current initiative, and it'll probably be 2 years to first demonstration, I would say, but the production system that we have, and as I was saying before, we've got an IP portfolio which covers a lot of the production processes that we've had to invent ourselves in order to realize these heat exchanger geometries. Our intention is to productize that production process. And so this will be an aggregation of some existing technologies, some technologies and machines that we've had to invent and that we create ourselves. And then we'll tie it together with a software operating system that will manage user authentications and IP and be a secure contract for commercial production, etc., etc. And then that production system will be, ideally quite a volumetrically efficient production demonstration line that can then be transposed near to point of assembly and near our customers' assembly lines, or in their tiered supply chain, and that can be run under license from Conflux. That's the sort of the next chapter, and that's really around this strategic theme of scaling for impact.
Interesting. A scalable blueprint to heat exchanger production powered by Conflux's IP experience and knowledge packaged into a software solution.
Yeah, I mean, there's
Awesome.
a software operating system that binds them all together, all the different parts. I mean, if you look at some of the additive manufacturing videos on YouTube, where it looks into some of the production halls of some more advanced AM-based production companies, you're seeing quite significant and large halls of production. Now, what we're wanting to do is have sort of a modular cell-based approach. We're pretty much tailored for a specific geometry. Like if a customer has certified heat exchanger with Conflux, and we've been providing through the product development process, and they say, okay, in 2028 or in 2030, we need to be producing 50,000 of these a year. Now we need to make decisions now about whether your solution, which has great performance and the price is right and all this sort of thing, but can it be produced at 50,000 per year? And what does that look like? How is that possible? And we need those 50,000 to be in California or in Texas or in Germany somewhere. How can we do that? Or should we go with another supplier now based on a different technology where that 50,000 is possible with all of the compromises, but it is possible and there is a clear path to that sort of level of production. Now, 50,000 heat exchanger, if the heat exchanger is, like the size of your hand, this is no small undertaking. If you think about it from an additive manufacturing technology perspective and where the maturity of that technology is up to, it's a considerable specific manufacturing facility for one application, for one heat exchanger design, producing, 50,000 a year. This is no small enterprise, and it doesn't exist now. Right? The designs are ours. We need to answer those questions from our customers, which is, how does it scale? How can we work with you now in order to scale to that sort of unit volumes in 4, 5, 7 years' time?
Kind of a perfect time to wrap this conversation up, to leave that number in people's mind, right? 50,000 highly complex, high performance heat exchangers produced in one facility. if somebody can do it, I'm sure Michael, you and the team can do it. Like I said in the beginning, I'm always inspired looking at your applications, at your heat exchangers. I was inspired when I left your booth at Formnext, and I am inspired now, just talking to you and understanding the complexity and the knowledge and the experience that you guys put into the development of heat exchange devices. So I really do appreciate you sharing your experience and story with us today. It was awesome to have you on the show. And I can't wait to see what's next for Conflux and the heat exchange market.
And thanks very much, Fabian. Thanks for having me.
And thank you out there for listening to our episode today. I hope you were just as excited and inspired as I just was by Michael's and Conflux's story. If you like this episode, please share it on Apple Podcasts or Spotify or YouTube or your favorite podcast platform. Also, you can leave us up to a 5-star review on all of these platforms and even leave comments if you have questions for Michael and Conflux. This was the Additive Snack Podcast. I'm Fabian Alefeld, and I will see you next time.